Welcome, everyone. Today, we're diving into one of the most fascinating challenges in computer science and mathematics, the Travelling Salesman Problem, or TSP. It sounds simple on the surface, but as we'll see, it holds some of the deepest complexities in the world of algorithms. Let's explore how we navigate this puzzle of optimization. Think about a delivery courier. Every morning, they have a list of cities to visit. The challenge seems straightforward. Visit every city exactly once, return home to the start, and do it all while minimizing the total distance or cost. It's a daily puzzle, but for a computer, the number of ways to solve it can get out of hand very quickly. To give you a sense of the scale we're dealing with, consider this. With just 20 cities, the number of possible routes is already astronomical. It actually exceeds the number of stars in our entire galaxy. This isn't just a big problem. It's a complexity nightmare that mathematicians have been wrestling with for decades. To solve this mathematically, we look at it through the lens of graph theory. We represent each city as a vertex. Those are the dots on the map. The roads or paths between them are edges. Finally, we assign a weight to each edge, which represents the distance, time, or cost of traveling between those two specific cities. The most obvious way to solve this is the brute force approach. You simply list every single possible route, calculate the total distance for each one, and pick the shortest. It's foolproof and systematic, but it has a massive flaw. It takes far too long. While it works for 5 cities, it would take a supercomputer billions of years to finish for just 50 cities. Why does brute force fail? It's all because of factorials. For n cities, there are n1 divided by 2 unique round-trip routes. This factorial growth is the villain of our story. Adding just one more city doesn't just add a bit more work. It multiplies the entire workload. By the time you reach 20 cities, you're looking at over 60 quadrillion possibilities. Let's look at this chart. As we add cities, the route count doesn't just grow, it explodes. Notice how the line starts to head almost straight up? This combinatorial explosion is why real-world logistics can't rely on simple trial and error. We hit a wall of complexity that requires a much smarter approach. Let's put some real time to these numbers. If you had a computer that could check 1 million routes every single second, 10 cities would be done in the blink of an eye. 15 cities would take about half a day. But 20 cities? You'd be waiting over 1,900 years for that same computer to find the best route. We clearly need a better way. So, the big question is, can we do better? The answer lies in not repeating our work. Instead of calculating the same path segments over and over, we use dynamic programming and a technique called memoization. It's about working smarter by remembering what we've already figured out. Dynamic programming follows a simple logic. First, we break the large route into smaller subproblems. Then we use memoization, which is just a fancy word for storing the results of those small paths in a table. Finally, we piece those optimal subpaths back together to find the overall best solution without ever recalculating a path twice. The standard dynamic programming approach for TSP is known as the held-karp algorithm. Instead of looking at full paths, it tracks the shortest way to reach a specific city, given a certain set of cities you've already visited. By focusing on these states, we drastically reduce the number of comparisons we have to make. We have to start thinking in subsets. We find the best way to visit a small group like cities 1, 2, and 3. Then, we use that known result to solve for a slightly larger group like 1, 2, 3, and 4. We build the solution layer by layer until we reach the final link that leads back to our starting city. The real power here is memory. The algorithm builds a lookup table of costs as it goes. When it encounters a subset of cities it has already solved, it doesn't do the math again. It simply pulls the answer from memory. This shifts the complexity from factorial to exponential, which is still large, but manageable for up to about 20 cities. Let's walk through the steps. We start with the base case, just the distance between pairs of cities. Then, we iterate through subsets, building up from 2 cities to 3, then 4, and so on. At every step, we only keep the minimum cost for that state. By the time we've checked all subsets, the global shortest path reveals itself. How much did we actually save? Brute force has a complexity of O(n), which is essentially unusable for anything beyond a handful of cities. Held-karp, our DP approach, brings that down to O(n) squared times 2 to the n. It uses more memory to store that lookup table, but it makes problems with 20 cities solvable in seconds rather than centuries. TSP isn't just an academic exercise, it's vital for global industry. Logistics companies use it every day to deliver millions of packages efficiently. It's used in manufacturing to find the fastest path for drills on circuit boards, and even in genetics to help scientists reconstruct DNA sequences. Every second saved is a huge win. But what happens when we have 1,000 cities? Even dynamic programming hits its limit. In those cases, we turn to heuristics. These are rules of thumb, like the nearest neighbor approach, which is fast but not always perfect, or genetic algorithms that evolve better routes over time. They give us a good enough answer very quickly. Let's take a quick moment to check what we've learned. Looking at the options on the screen, what is the primary reason the brute force approach to the traveling salesman problem is so difficult to scale as we add more cities? Is it logarithmic, constant, linear, or factorial growth? Take a second to think about it. To wrap things up, remember these 3 keys. First, TSP is a foundational problem in optimization. Second, permutations grow factorially, which makes simple searching impossible. And third, dynamic programming, specifically the held-karp algorithm, saves the day by remembering subresults and avoiding redundant work.